Why should we go into space? It won't solve any of our immediate problems on planet Earth, but it will give us a new perspective on them and cause us to look outwards rather than inwards.
Stephen Hawking always had something to say. He shook up the world of cosmology with more than 150 papers, dozens of which became renowned. He was told he only had a brief time on Earth, but spent half a century captivating audiences in lecture halls, on TV, and in the pages of his books. For newspaper editors, almost any utterance of his could make a headline, and he knew it. Hawking warned about the threats of nuclear war, genetically modified viruses, artificial intelligence, and marauding aliens. How is Stephen Hawking a genius? What is Hawking's theory of everything? And is it possible? Before we begin, make sure to smash the like button, subscribe to our channel, and click the notification bell for more amazing videos. Stephen Hawking is an English theoretical physicist whose theory of exploding black holes drew upon both relativity theory and quantum mechanics. He also worked with space-time singularities. Early life and education. Hawking was born on January 8, 1942, in Oxford, England. His birthday was also the 300th anniversary of the death of Galileo, a long source of pride for the noted physicist. The eldest of Frank and Isabel Hawking's 4 children, Hawking was born into a family of thinkers. The Hawkings, as one close friend described them, were an eccentric bunch. Dinner was often eaten in silence, each of the Hawkings intently reading a book. The family car was an old London taxi, and their home in St. Albans was a 3-story fixer-upper that never quite got fixed. The Hawkings also housed bees in the basement and produced fireworks in the greenhouse. Hawking was frequently on the go, with his sister Mary Hawking, who loved to climb, devised different entry routes into the family house. He loved to dance and also took an interest in rowing, becoming a team coxswain in college. Early in his academic life, Hawking, while recognized as bright, was not an exceptional student. During his first year at St. Albans School, he was 3rd from the bottom of his class. But Hawking focused on pursuits outside of school. He loved board games, and he and a few close friends created new games of their own. During his teens, Hawking, along with several friends, constructed a computer out of recycled parts for solving rudimentary mathematical equations. Hawking entered University College at the University of Oxford at the age of 17. Although he expressed a desire to study mathematics, Oxford didn't offer a degree in that specialty, so Hawking gravitated toward physics, and more specifically, cosmology. By his own account, Hawking didn't put that much time into his studies. He would later calculate that he averaged about an hour a day focusing on school, and yet he didn't really have to do much more than that. In 1962, he graduated with honors in natural science and went on to attend Trinity Hall at the University of Cambridge for a PhD in cosmology. In 1968, Hawking became a member of the Institute of Astronomy in Cambridge. The next few years were a fruitful time for Hawking and his research. In 1973, he published his first highly technical book, A Large-Scale Structure of Space-Time, with G.F.R. Ellis. In 1979, Hawking found himself back at the University of Cambridge, where he was named to one of teaching's most renowned posts, dating back to 1663, the Lucian Professor of Mathematics. A challenging life. In 1963, just shy of his 21st birthday, Hawking was diagnosed with motor neuron disease, more commonly known as Lou Gehrig's disease or amyotrophic lateral sclerosis, ALS. He was not expected to live more than 2 years. Completing his doctorate did not appear likely. Yet, Hawking defied the odds, not only attaining his PhD, but also forging new roads into the understanding of the universe in the decades since. As the disease spread, Hawking became less mobile and began using a wheelchair. Talking grew more challenging, and in 1985, an emergency tracheotomy caused his total loss of speech. A speech-generating device constructed at Cambridge, combined with a software program, served as his electronic voice, allowing Hawking to select his words by moving the muscles in his cheek. In a sense, Hawking's disease helped turn him into the noted scientist he became. Before the diagnosis, Hawking hadn't always focused on his studies. Before my condition was diagnosed, I had been very bored with life, he said. There had not seemed to be anything worth doing. With the sudden realization that he might not live long enough to earn his PhD, Hawking poured himself into his work and research. Just before his diagnosis, Hawking met Jane Wilde, and the two were married in 1965. The couple had 3 children before separating. Hawking remarried in 1995, but divorced in 2006. Bekenstein and Breakthrough. Hawking met his match at a 1972 physics summer school in the French ski resort of Les Hauts, France. Princeton University graduate Jacob Bekenstein thought that the second law of thermodynamics should apply to black holes too. Bekenstein had been studying the entropy problem and had reached a possible solution thanks to an earlier insight of Hawking's. A black hole hides its singularity with a boundary known as the event horizon. Nothing that crosses the event horizon can ever return to the outside. Hawking's work had shown that the area of a black hole's event horizon never decreases over time. What's more, when matter falls into a black hole, the area of its event horizon grows. Bekenstein realized that this was the key to the entropy problem. Every time a black hole swallows matter, its entropy appears to be lost, and at the same time, its event horizon grows. So, Bekenstein suggested, what if, to preserve the second law, the area of the horizon itself is a measure of entropy? Hawking immediately disliked the idea and was angry that his own work had been used in support of a concept so flawed. With entropy comes heat, but the black hole couldn't be radiating heat. Nothing can escape its pull of gravity. During a break from the lectures, Hawking got together with colleagues Brandon Carter, who also studied under Schema, and James Barden of the University of Washington, and confronted Bekenstein. The disagreement bothered Bekenstein. These were 3 senior people. I was just out of my PhD. You worry whether you are just stupid, and these guys know the truth, he recalls. Back in Cambridge, Hawking set out to prove Bekenstein wrong. Instead, he discovered the precise form of the mathematical relationship between the entropy and the black hole's horizon. Rather than destroying the idea, he confirmed it. It was Hawking's greatest breakthrough: research on the universe and black holes. In 1974, Hawking's research turned him into a celebrity within the scientific world when he showed that black holes aren't the information vacuums that scientists had thought they were. In simple terms, Hawking demonstrated that matter, in the form of radiation, can escape the gravitational force of a collapsed star. Another young cosmologist, Robert Penrose, had earlier discovered groundbreaking findings about the fate of stars and the creation of black holes, which tapped into Hawking's own fascination with how the universe began. The pair then began working together to expand upon Penrose's earlier work, setting Hawking on a career course marked by awards, notoriety, and distinguished titles that reshape the way the world thinks about black holes and the universe. When Hawking's radiation theory was born, the announcement sent shockwaves of excitement throughout the scientific world. Hawking was named a Fellow of the Royal Society at the age of 32 and later earned the prestigious Albert Einstein Award, among other honors. He also earned teaching stints at Caltech in Pasadena, California, where he served as visiting professor, and the Gonville and Caius College in Cambridge. In August 2015, Hawking appeared at a conference in Sweden to discuss new theories about black holes and the vexing information paradox. Addressing the issue of what becomes of an object that enters a black hole, Hawking proposed that the information about the physical state of the object is stored in 2D form, within an outer boundary known as the event horizon. Noting that black holes aren't the eternal prisons that we once thought, he left open the possibility that information could be released into another universe. Theory of everything. The Bekenstein-Hawking entropy equation is the one Hawking asked to have engraved on his tombstone. It represents the ultimate mashup of physical disciplines, because it contains Newton's constant, which clearly relates to gravity, Planck's constant, which betrays quantum mechanics at play, the speed of light and the talisman of Einstein's relativity, and the Boltzmann constant, the herald of thermodynamics. The presence of these diverse constants hinted at a theory of everything, in which all physics is unified. Furthermore, it strongly corroborated Hawking's original hunch that understanding black holes would be key in unlocking that deeper theory. Hawking's breakthrough may have solved the entropy problem, but it raised an even more difficult problem in its wake. If black holes can radiate, they will eventually evaporate and disappear. So what happens to all the information that fell in? Does it vanish too? If so, it will violate a central tenet of quantum mechanics. On the other hand, if it escapes from the black hole, it will violate Einstein's theory of relativity. With the discovery of black hole radiation, Hawking had pitted the ultimate laws of physics against one another. The black hole information loss paradox had been born. Hawking staked his position in another groundbreaking and even more contentious paper entitled Breakdown of Predictability in Gravitational Collapse, published in Physical Review D in 1976. He argued that when a black hole radiates away its mass, it does take all of its information with it, despite the fact that quantum mechanics expressly forbids information loss. Soon, other physicists would pick sides, for or against this idea, in a debate that continues to this day. Indeed, many feel that information loss is the most pressing obstacle in understanding quantum gravity. Hawking's 1976 that black holes lose information is a towering achievement, perhaps one of the most consequential discoveries on the theoretical side of physics since the subject was invented, says Rafael Buzo of the University of California, Berkeley. Among other attempts to develop a theory of everything is the theory of causal fermion system, giving the two current physical theories, general relativity and quantum field theory, as limiting cases. Another theory is called causal sets. As some of the approaches mentioned above, its direct goal isn't necessarily to achieve a TOE, but primarily a working theory of quantum gravity, which might eventually include the Standard Model and become a candidate for TOE. Its founding principle is that space-time is fundamentally discrete and that the space-time events are related by a partial order. This partial order has the physical meaning of the causality relations between relative past and future distinguishing space-time events. Causal dynamical triangulation does not assume any pre-existing arena, dimensional space, but rather attempts to show how the space-time fabric itself evolves. Another attempt may be related to ER equals EPR, a conjecture in physics stating that entangled particles are connected by a wormhole, or Einstein-Rosen bridge. At present, there is no candidate theory of everything that includes the Standard Model of particle physics and general relativity, and that, at the same time, is able to calculate the fine structure constant or the mass of the electron. Most particle physicists expect that the outcome of the ongoing experiments, the search for new particles at the large particle accelerators and for dark matter, are needed in order to provide further input for a TOE. On March 14, 2018, Hawking finally died of ALS, the disease that was supposed to have killed him more than 50 years earlier. A family spokesman confirmed that the iconic scientist died in his home in Cambridge, England. On May 2, 2018, his final paper, titled A Smooth Exit from Eternal Inflation, was published in the Journal of High Energy Physics. Submitted 10 days before his death, the new report, co-authored by Belgian physicist Thomas Hertog, disputes the idea that the universe will continue to expand. That's it for today's video. Don't forget to smash that like button, share this video with your friends, and tell us what you want to see next in the comments section below.